welcome back. This is 12.1 and Math 0965. And today we want to look at something a little bit different, the exponential expressions. All this stuff is really interesting because it's related to mathematical modeling. So the kind of math that they did for maybe the pandemic, this is at the heart of it. Okay, so this is going to be really good for everybody involved, I think, to learn something about. So anyways, the definition of an exponential expression, let's get my pen into black ink. Definition. It's like the reverse of what we're used to with polynomials. So before you would have seen things like y equals x to the third. Now you kind of reverse the exponent and the base, right? So now you can have stuff like y equals 3 to the x. Okay, see how I swapped those two? Right, so that's kind of the idea. In general, though, the definition it'll be given in one of two forms: f of x equals b to the x, where b is a base and x is the exponent, or you could just say y equals b to the x. There are some restrictions on b because we can't take like square roots of negatives and things like that. So they're always going to throw in some restrictions to make sure everything's on the level. So b is greater than 0, b is not equal to 1, x can be any real number, and then again b stands for base. Let's look at the first problem over there in WebAssign. You see to the right, and all you need to do is just make sure you can punch these things into your calculator. So I have 7 to the 2.6. I have a TI 30X sitting on my desk here. I'm going to see if I can figure this out. So where is my exponent button? So there's going to be a caret button. So I'm going to type in my calculator 7, and then I'm going to hit that caret button, and then I'm going to write 2.6. Sometimes I'll put the parentheses around the exponent, especially if there's a negative in there. So that was supposed to be a parenthesis button. It's a good practice, but for this particular example, it's not necessary. So anyways, let me try it. 7 to the 2.6, and I'm getting 157 point something. Make sure you round to where the computer wants you to round. It's saying 3 decimals there on the right, so 157.491. Okay, great. They're going to throw some more challenging ones in there, like problem 2. We have 8 to the square root of 8. Okay, and for this guy, then I would type in 8 and then hit caret, and then so let's see how I'm going to do this. 8 to the looking for my square root button. Apparently, I have to hit a second button to get that. So second square root, and then 8, and then I have to end parentheses. So in my calculator, I have to hit the second key, and then if you hit the x squared key above it, because you hit the second key, it's going to input that square root symbol. Okay, and then after you click that, it'll automatically give you a parentheses, and you just type 8, but you have to end the parentheses. The computer's not that smart. And what I mean by a computer's not that smart, it's not good at reading in between the lines, right? It's not good at knowing just kind of what you mean. Like if you talk to a person, you don't have to speak perfect English, and odds are they're going to know what you mean. A computer doesn't do that. A computer is literal. It doesn't really know what's going on in your life, so it's going to screw up if you're not perfect. And you kind of have to know your calculator, know how it operates in order to get the answer. Anyways, I put that in, I press enter, I'm getting 358.364 to 3 decimals. Okay. Alright, so there's problems like that. Let's see if there's anything else. Negative. This thing right here, let's look at this one. This is, I guess, problem 5 in what my math lab. They have this thing e to the negative 0.07. That number e is like the number pi. You guys heard of pi, 3.14. particular thing. Oh, great. So I hope you could hear me. My stupid microphone was up. I don't want to go back through and start all over, so hopefully you could hear me. I'm sorry if all of a sudden I got a lot louder. It's because my stupid microphone was up. So what are we doing? We're putting exponential expressions into the calculator. This thing, that number e, is like the number pi. And to get the e, what you have to do, again, is hit the second key on your TI-30X and then hit the ln key. And we're going to talk about what the ln is in this chapter. So ln, and what the ln does above it, it'll have this thing, and that's what you want. Okay, so you'll hit, let me clear second, and then ln, and it gives you e caret parentheses, and then inside the parentheses you put negative. Don't put the minus sign, you have to put a negative sign, and then 0.07, and then end parentheses, and push enter. All right, so it's going to automatically do that, and then I put the negative symbol, so you can't use the minus symbol, you have to use the negative symbol, and then I typed in 0 and 7, and then I had to type in another parentheses because computer, and then I hit enter, and I got 0.932. Okay, so just make sure you know how to use your calculator before the day of the test. I remember back before the pandemic, students said, how do I use my calculator? You're taking a test. So make sure you know how to use your calculator. Okay, graphing these things, you're going to spend a lot more time worrying about graphing in this chapter. And in pre-calc, you really make a big deal out of it. In the beginning, what you're going to do is just make a table. And then you kind of learn how to do these things called translations that are based off the form of the function. So they're going to kind of really beat you up over those issues. And looking at problems 11 to 16 here on the right, that's exactly what they're doing. So let's look at, the first one. These are problems 11 to 16. I'm just going to write 11 to 16. And the first one is f of x equals 8 to the x. Okay, so this will give you kind of a standard form for what these things look like. Unfortunately, this is kind of a big number, so I may have to kind of cheat a little bit. So x and then f of x, I'm making a table. Usually if you just go from -2 to 2, and the homework will tell you that, right? So it's saying, if you read the thing, and hopefully you could see me highlighting there, select integers from -2 to 2. Inclusive means you include -2 and +2. So -1, -2, -1, 0, 1, 2. And then you just put these things into f of x. So it'd be 8 to the -2. Exponent rules means that's the same as 1 over 8 squared. That would be 1 over 64. 8 to the -1. It's the same as 1 over 8 to the +1, which is just 1/8. 8 to the 0 is just 1. 8 to the 1 is 8. And then 8 squared is 64. Okay. All right, so I'm going to go over here and draw that thing. So 1, 2, 1, 2. So at negative, and I'm going to have to cheat a little bit on my 1, 2, 3, 4, 5, 6, 7, 8. I'm going to cheat a little bit by kind of doing one of those jobs, and then maybe way up here is 64. Okay, but yeah. So -2 is 1/64. That's getting close to 0, and then 1/8. So it's getting a little higher. 0, it's 1, and then at 1 it'll jump up to 8, and then at 2 it's way up there at 68. This is the kind of standard idea of the exponential curve. It just kind of goes straight up really, really quick. So you may have heard people in the news say exponential growth. That's what that means. Okay, so it's just going up, and it should be, my curve should be kind of more like a ramp. Okay, so I'm sorry that my plots aren't perfect. I apologize on behalf of the math community. On behalf of all teachers everywhere. Anyways, it should be kind of smooth like a ramp, okay? And then it just keeps shooting up, and that's exponential growth, okay? Okay, so this is kind of your basic form. And then all these other ones that they're having you graph are just kind of translations of this form. So what you'll learn eventually is that you can, once you know kind of the standard form, to get the other graphs, all you have to do is take this graph and kind of move it around, maybe flip it upside down, flip it around the y-axis, and it's easier than plotting all the points. Okay, so you'll be able to get around point plotting if you kind of learn this method of translations, and that's kind of what they're trying to push in this problem. Okay, they're trying to push you towards that end. So for example, if you have f of x equals 8 to the x minus 1, and of course again you could do a table of values. Okay, so again I'll go from -2, -1, 0, 1, 2, and I'll have 8 to the -2 minus 1 is -3, which is 1 over 8 cubed, which is, there's 1 over 8 cubed. 1 divided by 8 to the third is 1 over 512. Really close to 0, right? And then 8 to the -1 minus 1 is -2, so that's the 1 over 64. Put in 0, I get 8 to the -1, so that'll be 1 over 8. Plug in 1, I get 8 to the 0, which will be 1, and then plug in 2, I get 8 to the 1, which is just 8. Okay, if you just look at the coordinates, what's happening here is that these y coordinates are basically just kind of pushed over, right? So what's going to happen to the graph visually is that the entire graph is going to be moved over to the right by 1 unit. Okay, so we can again kind of draw this thing. And again, bear with me, 1, 2, 3, 4, 5, 6, 7, 8, and then we'll cheat a little bit and go up to 64 somewhere. Okay, so -2 is really close to 0, then -1 is a little higher, and then at 0 it's 1/8, and then at 1 it'll be 1, and then at 2 it jumps up to 8, and we have this picture. And you see all it is basically, yeah, for the above graph, all we did was move this guy over. Okay, so this graph is just the original graph shifted over, to the right by 1 unit. Okay, so they're really going to rake you over the coals here. Let me do 1 or 2 more of these examples, and then we'll carry on. So another one, f of x equals -8 to the x. So later you'll learn if you put a negative out in front of the function, what's going to happen is that it's going to rotate the original form about the x-axis. So it'll take this huge object and just rotate it around. And so if the original looks like this, the end object is just going to be like this. Okay, so it rotates that around the x-axis. Okay, so let's verify that, right? Let's, you know, are you making this up? Let's see. Seeing is believing for most people. So sometimes it's better not to see. I'll take your word for it. Okay, so it's okay to say that every once in a while. So it's a lot smarter sometimes to just take people's word for it. But anyways, -8 to the -2 is -1 all over 64. -8 to the -1 is -1 over 8. -8 to the 0 is -1. -8 to the 1 is -8. -8 squared is 64. -64. So remember some of your exponent rules. If you have -3 squared, what is that? That's like -3 times -3, which is 9. If you have -3 squared like this, then the base is just 3. It's not -3, right? That -1 is kind of apart from the base. So in this case, it would be -1 times 9, which is -9. Okay, so just a reminder for you guys. All right, let's go ahead and graph this thing and see what happens. This time I know it's going to be going kind of downwards, and so I want to graph that. 1, 2, 3, 4, 5, 6, 7, 8, cheating, and then 64. Negative. Okay, so negative 2, negative 164, negative 1, negative 1/8, 0, negative 1, 1, negative 8, and then 2. The cat is, oh my God, really? Sorry about that. Negative 2, negative 64. The hazards of working from home. Okay, so going like this, and you see it's just, it's the upside down version of the original graph, so wonderful. Let's see what else. And like I said, they're really going to rake you over the coals and make you go through every one of these and kind of study the behavior of the resulting graph. Okay. So yeah, graphing becomes a much bigger deal here, and then later on when you take like college algebra or pre-calculus and stuff like that. Okay, again, they're making sure you're able to evaluate exponential functions and their applications. So in example 1, what are we dealing with? They give you exponential function, models the average amount spent in dollars at a shopping mall after X hours. So I guess there are mathematicians working for shopping malls modeling the amount spent. It's all about splitting hairs these days. You want to make sure you're not wasting money. So you need people to study this kind of stuff. What's the average amount spent to the nearest dollar after 4 hours? So very simply, all you have to do is plug in a 4, and then make sure you know how to type this into your calculator. 1.56 to the 4th. So I would type in 42.2, and then either hit the multiplication symbol or hit parentheses 1.56 and then caret to the 4th. Okay, so make sure you can type these in, and make sure you get the same answer as what I'm going to get, and I hope I'm right. 249, let's take it to the nearest cent, 0.93, $249.90. Really? If you that's a lot of cash for, I don't think I've ever spent that much money at the mall. Okay, well, whatever. So just making sure you know how to, the graphing, again, more exponential functions. Let's look at graphing a fractional exponential function, like this example here, example 3 in the book. See what that looks like. Example 3. G of x equals 1/2 to the x. Okay, so let's do a little chart. I'm just going to go from -2 to 2. I'm not going to get carried away like the book does. All right, so -2, -1, 0, 1, 2. My little table, get 1/2 to the -2. Our exponent rules, if you've forgotten, if you have a to the b to some negative power, you could just flip it and it'll be to the positive power on the outside. You could pull that trick. Okay, so 1/2 flipped is just 2, but then you have to change the exponent to a positive. All right, so you get 4. 1/2 to the -1. So you flip 1/2, it'll give you 2 now to the positive 1, which of course is just 2. 1/2, anything to the 0th power except 0 is 1. 1/2 to the 1 is just 1/2, and then 1/2 squared is 1/2 times 1/2, which is 1/4. So let's get a picture of this character. I think the hard part is just kind of remembering all the exponent rules, and hopefully you get a lot of practice in this section. So -2, we're up at 4, -1, we're up at 2, 0, we're up at 1, 1, we're at 1/2, and then 2, I'm at 1/4. So what they're going to call this as a model is exponential decay. So the amount is decaying towards 0 over time. You may have heard that when they're talking about radioactive materials. We'll talk about carbon dating later on. So yeah, good stuff. Let's take a look at, let's see what the homework kind of stuff, if there's anything in here I want to look at.
I think we're okay for a second. I took some of these problems out. I just thought there were so many in there, it was getting ridiculous. So just for the sake of sanity, I went ahead and just removed some. All right, so anyways, so let's take a look at the next section in the book is characteristics of these objects, right? So you could study the characteristics of like a parabola, get the y-intercepts, the x-intercepts, the domain, the range, the vertex, all that stuff. We kind of want to identify all that material here with exponentials. So characteristics of exponential functions. In particular, when there's like nothing in front of the b, and then you have so f of x equals b to the x, or y equals b to the x. So first off is the domain, and the domain is all real numbers, and that just means you can put anything into that function and evaluate it. Okay, you don't have to worry about division by zero or radicals with negatives or anything. Okay, secondly, then the range. Okay, so if you think about the picture, okay, so here's the kind of the standard issued exponential function. The range, it kind of starts at 0 and then goes off to infinity, the y values, the possible y values, but it's never going to hit 0. There's nothing you could put into that function that will cause the output to equal 0. So the range is going to go from 0, not including 0, to infinity. It doesnthis have an x-intercept, but it does have a y-intercept, right? So it's going to hit right here. If you look on the right at the picture, this is the y-axis, this is the x-axis. The y-intercept is when x is equal to 0. Okay, so when x is equal to 0, you'd have b to the 0, which would be 1. Okay, so the x-intercept is, in these cases, 0, 1. Then, of course, the forms, right? And the form is based off, believe it or not, that b value. Because in this previous example, you may not have noticed, but you could write 1 over 2 is 2 to the negative 1 to the x. And then from the exponent rules, this is 2 to the negative x. And if you think about what 2 to the positive x looked like, 2 to the positive x was this. Okay. So 1/2, if the base is a fraction, what really is happening is it kind of rotates it around the y-axis, and you have decay. So in the book they'll say, all right, when the b is not a fraction, in other words, when it's greater than 1, you're going to have kind of the standard ramp look, the exponential growth. But if b is a fraction, so if b is greater than 0 but less than 1, you're going to have the rotated version, right? It's going to decay over time, and that's just a terrible looking graph. It should have kind of a bowl shape to it. I apologize on behalf of the math universe and teachers in general. I don't know why I'm apologizing for that. I apologize. I don't know. I'm sorry. Okay. So anyways, there's those. And then as far as asymptotes go, it does have an asymptote, but you just can't see it, right? The asymptote is at y equals 0. So there's always this asymptote, and if you move the graph up and down, you'll kind of see the asymptote. So we'll look at some examples maybe where we're adding a little bit to the graph and it'll shift up, and you'll see the asymptote kind of pop up. Okay, so it does have an asymptote, although you can't see it. It's a horizontal asymptote at y equals 0, right? Okay, great. So let's look at some more graphing then. The book, the homework just loves to force you to graph things at this point. It's just obsessed with graphing, right? So let's kind of take a look here. Maybe we can find something interesting. Maybe not. Okay, this one's kind of interesting. So graph the functions. So this is, I guess, question 14 in my math lab. F of x equals 3 to the x, and then f of x equals 3 to the x minus 3. Okay, all right, so let's investigate. This is actually g of x. Okay, so I'm going to do the ordered pairs on this dude first. So I got -2, -1, 0, 1, 2. Plugging in my exponents. 3 to the -2 is 1 over 3 squared, which is 1 over 9. 3 to the negative 1 is 1 over 3 to the positive 1, which is 1 over 3. 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. Let's get the other one kind of out of the way as well while we're here. Okay, so negative 2. If you look to the left, you already kind of have part of the answer, right? The g of x is going to be 3 to the negative 2 minus 3. 3 to the negative 2 on the left there, I already figured that out. That's 1/9. So I could cheat a little bit and just put 1/9 there. And then minus 3, I need a common denominator. 3 is the same as 3 over 1. And if I multiply top and bottom by 9, I'll get 27 all over 9. So this will be negative 26 over 9. Okay. All right, negative 1 is going to be 3 to the negative 1 minus 3, which is 1/3 minus 3. 3 over 1, multiply top and bottom by 3 to get a common denominator. That'll be negative 9/3. So I'll have negative 8/3. 0 will be 3 to the 0 minus 3, so 1 minus 3 is negative 2. 1 is 3 to the 1 minus 3, is 0. And then 2, 3 squared minus 3 is 9 minus 3, which is 6. Okay, so we want to graph both of these guys in the xy plane. Okay, so 1, 2. And I could tell I need to go down a bit. What is that? Probably like a 2 point something. So I need to go down a little, just a little bit. Then 1, 2, and I need to go up to 9. 2, 3, 4, 5, 6, 7, 8, 9. Okay, so f of x at negative 2, it's 1/9. Then it goes up to 1/3. Then it goes up to 1. Then it goes up to 3. Then it goes up to 9. Okay, so there's our first graph. Let's put that guy in red. Let's use some colors, right? Oh my god, my chair just broke. Oh god. Sorry about that. Freaking A. Wonderful. Alright, so anyways, there's that. That was a beautiful curve right there. Even amongst all of the chaos, I managed to draw a very nice exponential growth function. Okay, the other guy, negative 2, negative 26 ninths is like negative 2 something. Negative 8/3 is a little higher. 0, whoops, is right here. 0, negative 2. So let me undo those. All right, so 0. Crud. So I didn't go far enough down. I need to go down to 3. Sorry. All right. So anyways, negative 2, negative 2 point something. Negative 1, negative 2 point something, but a little bit higher. 0 is negative 2 right there. 1 is really 0. Really? Okay, whatever. And then 2 is at 6. 1, 2, 3, 4, 5, 6. Okay, so go ahead and graph that then. You see you have this blue kind of curve this time. And it's exponential growth. But anyways, what's the kind of connection between these two pictures? And that's what they'll ultimately start asking you. How are these two connected? Well, the second graph is just the first graph shifted down by how many? Well, shifted down by 1, 2, 3, right? 1, 2, 3. My tick marks aren't all that great, so it's not exactly the best picture, but yeah, that's it. And you can kind of see that coded into the expression, right? So look at g of x. It's 3 of x minus 3, and g of x is just f of x shifted down 3. So after a while, you're going to be able to identify kind of the new picture if you just know the basics, the basic forms of the original pictures, right? So I'll note f of x is just, g of x is just f of x shifted down 3. Okay, and of course on the graph over here, I think that's this guy here. Yay! All right, so wonderful. So interesting stuff, isn't it? Isn't it cool? It's kind of cool. All right, then we have some applications of exponentials. Where do you see these things? For like thousands of years, they've literally used these things in determining financial stuff. So a lot of the origin of language and math comes from bookkeeping and taking a record of accounting matters. Okay, so the first kind of recorded use of this number e, which is what I'm actually talking about right now, the natural base e, which is kind of like the number pi. The first recorded use of this thing in exponential expressions was in bookkeeping. Okay. What is the number e? It's like 2.71828 blah blah blah, like 3.14159 I think is pi. E has that same sort of format. So it'll come up then in financial matters, in particular compounding interest. So compound interest and interest, and there's formulas that will give you for these. The annual formula, which you may have seen in 095, is A equals P times 1 plus R to the T. Okay, so what does this tell you? This tells you if you put a certain amount into a bank, like P, which they call the principal, over a certain amount of time T, which we're going to give this in years, if you have an interest rate of R, which in the formula will be given as a decimal, but usually in the story problem given as a percent, if you have some interest rate R, your future amount will be A, and it's computed using this formula. Okay. So at the end of the year, they figure out how much interest the original amount has accumulated, and then they just add that into the into your bank account, and then they keep on repeating that. Okay, you can have different kind of compounding periods. So if you have compounding n times a year, the formula for that is A equals P times 1 plus R over n to the nt. But if you have continuous compounding, so you compound every nanosecond, that's where you're going to see the number e. Okay, and it's a weird kind of phenomena that you'll study if you take calculus. When you get to calculus, if you do take calculus, you talk about infinity. That's really the only deal in calculus. Is you're allowed to talk about infinity. And when you take the number of compounding periods per year and let it go to infinity, this number e kind of rears its ugly head. Okay, so you'll see that in the formula. So anyways, let's look at one of these WebAssign problems, if I can find the thingamajig. Oh, the second part of the question, it was asking me, the graph of G is obtained by shifting the graph of F 3 units down, right? And then, so they're kind of already pushing you in that direction to kind of analyze the differences between graphs. Okay. This one here is more complicated. I don't have time to go through it, but if you have kind of the 3 to the x plus 1 minus 2 here on the right, what is that going to do? It's going to shift it to the left by 1, and then it's going to go down 2, I believe. Okay, so it's going to have more than one shift. So it can go up and then down, up and then right, and then do a flip, all kinds of things like that. And after a while, you'll learn an order of operations for that. Anyways, let's look at this problem. So it's kind of a story problem based off compound interest. It's number 18 in my math lab. The value of the investment is $10,000. So find the accumulated value of an investment of 10 grand. So P is equal to your 10 grand. It's going to be put in the bank for 3 years, so T is 3. The interest rate is 6.5%, but you need it as a decimal for the formula. So you move, if you have 6.5%, you move the decimal over 2 places. So the rate in decimal form 0.065. First, we want to figure out the accumulated amount if it's compounded semi-annually. So semi-annually means n equals 2. Okay, so twice a year. So A would equal 10,000 times 1 plus 0.065 all over 2 raised to the 3 times 2, which is 6. Then you need to plot that into your calculator. You're going to need some parentheses action. So I put 10,000 times parentheses 1 plus 0.065 divided by 2, end parentheses, then caret, then 6. Push enter, and the accumulated value looks like $12,115.47. Okay. All right, part B. What's the accumulated value if the money is compounded monthly? So there are 12 months in a year, so n is 12. So A will equal 10,000 times 1 plus 0.065 all over 12 raised to the 3 times 12, which is 36th power. Okay, so I'm going to go 3,000 parentheses 1 plus 0.065 divided by 12 raised to the 36th power, and I'm getting $12,146.72. Okay, so the more compounding you have, the better it is. If you go to the bank, you want more compounding, and the best compounding is the continuous compounding, right? So in the third case, they want to know what happens if you have continuous compounding. You may think you're going to have like tons of millions of dollars. If, well, it's compounding every nanosecond, I must be a millionaire now. No, it doesn't work that way. There's kind of a maximum amount that you can accumulate. So let's see what we get, right? So 10,000 times e to the RT, right? So I call this the Pert formula for that reason, Pert. There used to be a shampoo called Pert. I don't know if they still have that, but so one way to remember formulas is just to make words out of them. If you learn alphanumerics, that becomes even cooler because you can make words out of numbers. So there's special ways to make words out of numbers. So like the number 1, you just think of as L. I forget how it all works. 9, you kind of think of as P because it looks like a backwards P. And you don't use letters. You kind of make up your own letters. So if you want to memorize the number 19, you could say it's loop. So this would equal loop. Okay. And then if you have a big formula with a bunch of letters and then numbers as well, you could use alphanumerics plus this idea of just making words out of the letters, and you're able to memorize your formulas that way. But that's only if you get in a discipline where you're doing tons of memorizations of formulas, like maybe I had to do in grad school and stuff. But yeah. So just a side, I'm sorry, 10,000 times E, so I'm going to go second, and then ln. E to the, I guess it was 36, right? R times, no, it's R times T, so 0.0065 times T was 3. Okay. And I'm getting, so you should get something similar, right? So it's anyway 0.065, and I had to put all of this in parentheses in my calculator, times 3. So when I typed it in, it was like this. I had to hit the second button and then hit the LN button, and then I put in the the 0.065 times 3, blah blah blah, and then I had to hit a parentheses, and then I hit enter, and I got 12153.11. So you see, it's not like you got $1 million, right? It's only a little bit more than monthly compounding, but you always want to push for continuous compounding. Okay, long story short. Great. So there's that business. Is that all we have to worry about here? Pretty much. So some extra graphing problems here at the end. domain. So if you look at this graph, what's the domain of it? You can kind of guess. I mean, the domain of the exponentials is always going to be negative infinity to infinity. Hit the infinity button down there. What else? What's the range? You can kind of look at the graph and see the y values. It's just going from -3 to infinity. It never hits -3 though. It gets really, really close to it, but it never hits it. So in your answer, you would put parentheses, -3 to infinity. Okay. You check your answer. Yay. I guess I didn't do a video quiz yet, so let's do a video quiz here. Just, let's make this the video quiz. I guess it's a bit silly, but problem 22, this is the video quiz for 12.1. Let me mark it down in my notes. Oh, got one pencil here and it's broken. 12.1 video quiz number 22 from my math lab. Okay, so what's the domain of this thing? Of course, the domain for all of these guys is just going to be infinity to infinity. Okay, so negative infinity, that is, to infinity. Then the range is probably going to ask for it. You can just look at the graph. It looks like it's going to go from 0 to infinity, right? So 0, not including 0, so you use an open parentheses there. Whoops, put in some extra stuff, to infinity. Yay, fantastic. Okay, so range then is just 0 to infinity. That would be your answer for that video quiz. Okay, I think that will get you through the work, I hope. Tons of graphing, like I said, and then some applications where you're basically just doing some substitution there. And I think this is just another substitution. And then some more substitution. And some more substitution. This model is called the Logistic Model, and this one is used to model pandemics and stuff like that. So maybe we should take a quick look-see at it. This is problem 31. It's called a logistic equation. That type of curve you see over here, you see how it looks like an elongated S? They call that a sigmoid. And it's used a lot, not only in the modeling of pandemics, but in the model in what they call neural networks, which is used in machine learning, which you may have heard of called artificial intelligence, stuff like that. They use these formulas, so they use them. Yeah, I'll just leave it at that. Sorry, I won't elaborate. So this function describes the number of people who become ill with a virus T weeks after the initial outbreak in a town of 30,000 inhabitants. The horizontal line on the graph shows you the limit to the exponential growth, the epidemic growth. So in exponential growth, the population or the number of people who are infected goes off to infinity. It just keeps going up and up and up. And that's unrealistic because we have finite populations, right? Once everybody in the population has the disease, then there's nowhere else for the disease to spread. Unless you have this case where people are getting better and no longer have the disease. That's a whole different ballgame, right? So there's always this trade-off with realism and then complexity. The more real it is, the more complex the formulas have to be. So this is one step up in realism from your exponential growth. So anyways, how many people became ill with the virus when the epidemic began? So for that, all you have to do is figure out n of 0 times 0. And if you don't like the idea of thinking of pandemics, you think of zombies or something. That always helps. Kind of take away the realism. So after at time 0, how many zombies are there? It's that kind of idea. We're gonna have to round to the nearest person. So let's take a look here. This would we have 30, 1, 2, 3 divided by 41. I think I put 300,000 in there, and I put an extra division symbol. 731 people, I guess, were originally infected. or 732 people in the town. Okay, so I don't know, maybe I don't know how that could happen. That one outbreak movie, like a pilot crashes in the swamp, and they find it, the parachuted body, and he has this vial with him or something, and it gets into the water. So you can imagine 700 people drinking the water and actually getting infected with this zombie virus or whatever it is. So in this case, there were 732 people originally infected with the zombie virus. Check answer. Yay. How many people will be ill at the end of the second week? So plug in 2. So you get 30, 1, 2, 3, all over 1 plus 40 e to the negative 2 times 2 is negative 4. So I got to do a little bit of calculator work. So I type in 30,000. 30,000 and then divided by, and then I have to hit parentheses, right? So it'd be 1 plus 40 e and then caret. So e you have to hit second ln, and then you have to hit caret negative 4. Okay, make sure you can type that into your calculator. All right, so clear 30, 1, 2, 3 divided by 1 plus 40, and then second ln, and I got negative 4 inside there. So it looks like a lot. Jeez, oh man, this thing spreads like bananas. 17,315 people. Okay, 17,315 people. Fantastic. Okay, I guess, well, that's it. And then there's more. Why can't the spread of the epidemic simply grow indefinitely? Well, there's only 30,000 people, so the number of ill people cannot exceed the number of people in the town. And then I must have got rid of that one, and that's it. Okay, great. Thank you for watching as usual, and I will see you next time.